Hello everyone. I am here to present an e-content on the topic Simple Bifurcations from the course Nonlinear Dynamics. I am Dr. Ansima Joseph, Assistant Professor, Research Center of Physics, Fatima College, Madurai. So, what are the learning objectives? By the end of this video, you will be able to define what is bifurcation, identify the different simple bifurcation types from its mathematical forms, and also analyze the stability through phase portrait and bifurcation diagrams. So I am planning to give this content in 3 modules. So here we will see a short introduction about bifurcation. And then in part 2, we will see the first 2 types, saddle node and transcritical. And in part 3, we will see the pitchfork and harp bifurcation. So what is bifurcation? The literal meaning of the term bifurcation is division into 2 branches. Here you can see the river streamlining into 2 divisions. In mathematics, this term has got a deeper meaning. It says that when a small change in the parameter of a system causes a sudden drastic change in the dynamical behavior, then a bifurcation is said to have happened. Now, it is possible in both in continuous systems described by ordinary partial or delay differential equations, or even in discrete systems described by maps. Here you can see an animated picture wherein the phase portrait describes a bifurcation. That is, as the control parameter changes from 0.5 to 0.1, there is a drastic change in the flow. So a bifurcation is said to have happened here. And as we proceed, we will identify that this is a type of bifurcation called saddle node bifurcation. So this term was introduced by the mathematician Poincare in his first paper in Acta Mathematica. So before getting into the simple types of bifurcation, we would have to see some key words like fixed point, phase portraits, bifurcation diagrams, stability, stable and unstable fixed points. So all these things we will see here. So what is a fixed point? A fixed point of a dynamical system, say it is defined by an ordinary differential equation like dx by dt is equal to f of x, is a point where the system does not change over time. That is, you make f of x equal to 0 and identify the solutions of it, which you call it as x star, the fixed point. It is the resting state or the equilibrium points of the system. And if you have identified the fixed points, the next question is, are they stable or unstable? So how do we determine that? If the nearby trajectories are moving towards it, then you call it as an attractor, a stable fixed point. And if the trajectories are moving away from it, you call them as a repeller, the unstable fixed point. But how do we see this mathematically? So you will have to get the differentiation of f of x, and substitute the fixed point into that. So when f prime of x star is less than 0, you call that as a stable fixed point. And if it is greater than 0, then it is an unstable fixed point. Now, how do we see this geometrically? Yes, we do have a geometric way of thinking this stable and unstable fixed points. How is that possible? Consider a simple nonlinear differential equation like x dot is equal to sin x. In order to solve this equation, what do? We adopt the separation of variables technique. That is, dx by dt is equal to sin x. Bring all the x terms on one side, t terms on the other side, do the integration and arrive at the solution. So this is the solution of this differential equation. But what about the fixed points? So here is a more physical way to think about the vector field. When we have a fluid flow, we can identify the velocity which is varying from place to place given by the rule x dot is equal to sin x. So when you plot x dot with x, you can identify the fixed points also. Those are the points at which the curve meets the x-axis. So how do we get them mathematically? You make f of x is equal to 0. So sin x is made to be 0 and you arrive at those x. So here it will be x is equal to 0, pi, 2 pi, 3 pi, etc. So the next question is, how do we determine their stability? So here we can see that there are so many circles. Either they are solid black dots or they are open circles. Solid black dots, they are the stable fixed points, and open circles are the unstable fixed points. And these solid dots, they will be attracting the fluid flow towards them. So the arrows will be towards them, and the unstable fixed points, they will be the repellers, in the sense they will direct the trajectories to move away from them. So the arrows will be moving away from them. Now, once we have marked the fixed points, how do we determine whether they are stable or unstable? That can be also done looking into the x dot behavior. So when x dot is greater than 0, then the arrows are pointing towards the right. When x dot is less than 0, the arrows are pointing towards the left. So what is the mathematical meaning? You take f prime of x, differentiation of x, and you identify where they are greater than 0 or less than 0. So when they are greater than 0, it is towards the right, and when they are less than 0, they are towards the left, and accordingly you can see where the trajectories are moving towards or away and determine whether they are stable or unstable. So now that we have learned what is a fixed point, when can we call them as stable or unstable, the next question is about the bifurcation point. So that is the next keyword. So what is a bifurcation point? It is the parameter value at which the dynamics of the system undergoes a drastic change. So suppose I am having a system described by the equation x dot is equal to sin x plus some mu t. So mu is the parameter. As the parameter mu is varied, the fixed points may be created or they may be destroyed, annihilated, or even they can undergo a change in their stability. They can get swapped or they can collide. So all these changes constitute the change in the dynamical behavior of the system. So this is possible if you change the control parameter, and that parameter is called as the bifurcation point. So how do we visualize this bifurcation? It is done with the help of two visual tools. One is the phase portrait, which is nothing but a geometric representation of all possible trajectories, the flows of the system. That is, you plot the velocity with respect to the position, x dot with respect to x. So x dot in y-axis and x in the horizontal x-axis. You get a phase portrait. What about the bifurcation diagram? It gives the system's long-term behavior with respect to the control parameter. So the phase portrait was plotted for a fixed parameter value, and here the parameter is going to get the varied values for which the system's fixed points will be plotted. So they are called as the phase portrait and bifurcation diagram. So here I have shown you two pictures. The first one, what is it? It is the phase portrait, because for a particular bifurcation parameter b is equal to 1, we have plotted dx by dt in the y-axis and x in the x-axis. Similarly, the second picture is the bifurcation diagram, where we have plotted x with respect to r, where r is the control parameter. The first plot we have got b, no? So that b, if we bring here as the x-axis, then it becomes the bifurcation diagram. So now that we have learned what is a fixed point, what is a stable or unstable fixed point, bifurcation point, then phase portraits, bifurcation diagrams. Now we are entering into the types of bifurcations. So we will look into some simple bifurcations called local bifurcations. What are local bifurcations? So here the change in the dynamical behavior, either through the change in stability or the number of fixed points, it is going to happen within a tiny specific neighborhood. So predictable local shifts. Also, it is going to get indicated through the change in the eigenvalues of the single point as the control parameters are getting varied. Now, what are the important local bifurcations which we are going to study? Saddle node, pitchfork, transcritical and hop bifurcations. So in this content, we have seen the very basic points of bifurcation. What is bifurcation? What are fixed points? When do you call them a stable or unstable? Bifurcation point, what is it? Then what are the visual tools? All these things we have seen here. Before getting into the part 2 module, where I will be introducing the basic types, that is the local bifurcations, think and answer the following questions. These could be the frequently asked questions from the content which we have seen here. So for a system represented by x dot is equal to r plus x square, how many fixed points exist? That is the question when r is greater than 0. So how do we do that? Make f of x equal to 0, r plus x square is equal to 0, x square is equal to minus r. So x is equal to plus r minus root of minus r. 2 points, 2 fixed points exist. So in bifurcation diagram, dashed line represents unstable fixed point. So find all the fixed points for a system described by the equation dx by dt is equal to x cube minus 3x square plus 2x, classify their stability and sketch the graph. So the trick is rewrite the equation as x cube minus 2x square minus x square plus 2x. Then you can take x out and write the equation as x into x minus 1 into x minus 2. So from this you can get the fixed points as 0, 1 and 2. When you plot the curve, you will identify when the graph is greater than 0, you mark the arrow towards the right. When it is less than 0, you put the arrow towards the left. So you can identify stable or unstable fixed point. So here you can see that the first fixed point, x is equal to 0, you have both the arrows moving away from it. So it is unstable. Then x is equal to 1, both the arrows are moving towards it. So it is a stable fixed point. X is equal to 2, both the arrows are moving away from it. Again, it is an unstable fixed point. So happy learning. I shall meet you in the part 2.